This film has been produced to show some of the activities, efforts, and achievements accomplished during the past year by the United States Air Force Aerospace Medical Research Laboratories in Dayton, Ohio. Prior to actual ejection from a high-performance jet aircraft, the stability of the seat must be determined. The seat is loaded aboard a cargo aircraft from which it will be dropped, occupied by a parachutist who had participated in its design. We see the seat and its occupant leaving the aircraft. The stabilization booms are already extended. In an actual ejection, they would be automatically extended as the seat separates from the aircraft. Red signal smoke generators are mounted on the booms for the purpose of facilitating photographic recording of this test. Observing the descent of the seat from the ground, we see the drogue parachute deploying at 15,000 feet or 4,600 meters. The main parachute starts to deploy, but in this particular test, it collapsed partially. The subject received an opening shock estimated at 16.5 G and lost consciousness. Fortunately, his reserve parachute was opened by the preset aneroid timer and separated him, still unconscious, from the seat. He regained consciousness a short time before landing and can be seen to be none the worse for his experience. Here we see the successful result of the preceding stability test and many others like it. This is an actual live ejection of the new seat made from an F-106 aircraft flying at 22,000 feet at a speed of 535 miles per hour. In this sequence are shown experiments of simulated weightlessness, or zero-G. To produce this weightless state, an aircraft, in this case a Convair C-131, is flown through a Capillarian trajectory. Starting at 12,000 feet, the aircraft goes into a 10-degree dive until a speed of 250 knots is reached. After a pull-up at 2.5 G, a 35-degree climb results in 15 seconds at zero-G. The maneuver ends lost under weightlessness. Pigeons normally keep their bodies in a horizontal axis while in flight. These zero-G birds have lost their feeling for what is up or down and point in all directions, some even flying upside down. Muscular efforts required for functioning in the normal gravitational field of the Earth will be greatly reduced in prolonged periods of reduced or zero gravity as encountered in orbiting or space vehicles. To produce a condition of reduced gravity for periods up to 24 hours, a human subject is completely immersed in a tank of water at a temperature of 92 3/10 degrees Fahrenheit. A helmet modified to permit intake of liquid food is worn. The subject attaches himself to the bottom of the tank to prevent his rising to the surface. Communication between subject and observer is maintained constantly. The subject has now completed his 24-hour run and after removal of his rubber suit will be subjected to several cardiovascular stress tests. Control values for these tests had previously been obtained. The tilt table test is one of the most sensitive indicators of the cardiovascular status. ECG electrodes are applied and blood pressures are recorded throughout this study. After obtaining baseline values in the horizontal position, a 12-minute test of orthostatic tolerance is performed in the vertical position. ECG and blood pressure are recorded at 1-minute intervals. At the 10th minute, the subject experienced syncope. His pulse rate is 184, blood pressure 98/96. Recovery is immediate upon tilting to the horizontal position. Next, the subject undergoes accelerative stress studies. Cardiovascular function studies are combined with psychomotor performance tasks to estimate arm strength and coordination under dynamic conditions. Heart rate is monitored. The test terminates when the subject fails to respond to the center light, indicating loss of central vision. The heat chamber test is another very sensitive and reliable indicator of cardiovascular capability. Tests are discontinued if the pulse rate reaches 150. In this test, the pulse rate rose to 135 after only 5 minutes. At 7 minutes, it stood at 145. The test was terminated at 9 minutes when the pulse rate reached 163. This test documents a greatly reduced tolerance to heat as a result of the 24-hour hypodynamic experiment. Finally, neuromuscular coordination is evaluated by using the complex coordinator. It is a light matching task using a control stick and rudder pedals to respond to roll, pitch, and yaw lights. The final score is an average of successful adjustments made during 10 successive 2-minute runs. In this test, no significant impairment of performance was observed as a result of the 24-hour immersion. The vertical deceleration tower is used to study the effect of impact on man and laboratory animals. The platform, which is being raised by a hoist, has a free fall distance of up to 30 feet and peak accelerations up to 75 G can be produced. As the platform is being raised, the tip of the 4-foot plunger can be seen below and at the back of the cart. And when the cart is dropped, the deceleration is caused by the plunger displacing water out of the cylinder. The drop cart can be seen through the window in the instrumentation room. When the subject is ready to be dropped, the project engineer presses the release button and the cart drops. The instruments record the accelerations and other physical data. To determine basic criteria to provide optimum protection against the abrupt acceleration of landing impact, the inclined test facility is used. The test vehicle being dropped duplicates the impact attenuation system and body restraint support system in the Project Mercury capsule. This apparatus consists of a simulated heat shield, a body support and restraint frame and columns of crushable aluminum honeycomb to attenuate the impact. The subject is impacting at a velocity of 30 feet per second, which simulates the descent rate of the recovery parachute system. The subject and the test vehicle are instrumented to measure both the acceleration input and the response of the subject at the head and sternum. The subject is restrained by a modified lap belt shoulder harness, a forehead and chin harness, and leg retention straps. The subject is supported by a fully contoured rigid body support, which provides a 12-degree inclination of the head to torso axis. These high-speed movies, 1,000 frames per second, illustrate the relative good body restraint and support provided within this system. This subject is experiencing a short duration acceleration of 49 G. This vehicle is descending at a rate of 20 feet per second with a horizontal velocity of 20 feet per second. The experiments were conducted within the past year as a part of a research program to study the landing impact problems associated with the B-58 emergency escape capsule. They serve to illustrate the scope of the landing impact problem and the capability of the inclined test facility. This is the vertical accelerator. The objective of this research facility is to determine the effects of severe buffeting on man as may be encountered in aerospace and space operation. The facility has a maximum acceleration of 5G, a vertical double amplitude up to 20 feet, and a frequency range up to 10 cycles per second. A performance test is being conducted by the subject being vibrated. Random movements are being programmed into the equilibrium chair, and the subject must correct these movements to maintain a zero position. A blindfold is used to eliminate the visual input of the subject's sense of equilibrium. The difference between the programmed movement and the correction is a measurement of the subject's ability to perform.